Ever get that feeling? Like you're just starting to wrap your head around something big, and then suddenly, boom, the rules change.
Uh-huh. Yeah, I know what you mean.
Well, buckle up, because today we're taking a deep dive into a real cosmic head-scratcher.
Oh, this is going to be good.
We're talking about some very recent findings, really
Yeah.
fresh stuff, coming from the Dark Energy Spectroscopy Instrument, DESI. And you know what they suggest? That the force that's been pushing the universe outward, this expansion we keep hearing about, well, that force, dark energy, might not be as constant as everyone thought.
Right. Talk about shaking things up. Decades we've been working with this idea of steady, unchanging dark energy. But now this initial data from DSI, well, let's just say it's throwing a bit of a wrench into things.
A big wrench, from the sounds of it. And that's exactly what we're here to do today. Unpack what DSI has found, why it's potentially a total game changer in cosmology, and ultimately what it all means for, well, everything. The big picture. Our guide for this deep dive is this article, Dark Energy May Not Be Constant, How This Discovery Can Change Science. It really gets into the nitty-gritty of the DESI results and all the massive questions they're raising. So, first things first, with something this monumental, what exactly is DSI? And why are its findings such a big deal?
All right, so DSI, it's this groundbreaking instrument located at the Mayall Telescope in Arizona. And what it's done, its main achievement, it's created the biggest, most complete 3D map of the universe that we've ever seen.
I read that it mapped 15 million galaxies. 15 million.
That's right.
It's mind-blowing. It's almost impossible to even imagine a number that huge. And the light, think about this, the light from the furthest of these galaxies has been traveling towards us for, get this, 11 billion years.
It's incredible.
11 billion years. We're looking back at the universe when it was just a baby, just a fifth of its current age.
Absolutely. So by charting the positions of this huge number of galaxies across these vast distances and across time, DESI is giving us this incredible, really unparalleled view of the universe's large-scale structure and how it has expanded over time. But the real key to unlocking all these secrets hidden within that map lies in something called baryon acoustic oscillations, BAO for short.
Oh, I was wondering when we get to those. BAO. Sounds kind of like, I don't know, a fancy cosmic echo.
Yeah, that's not a bad way to think about it. Picture the early universe, right? It was this insanely hot, dense soup of particles.
Okay, got it. Particle soup.
And sound waves, actual sound waves, they rippled through this soup. And they created these areas where things were just a bit denser. Then, as the universe started to cool down and galaxies began to form, well, they were more likely to form in these denser regions, these spots where the sound waves had left their mark.
Makes sense.
And this whole process, it left behind a specific pattern, kind of like a Perseid distance between galaxies. Imagine ripples, but they're frozen in place. That characteristic distance, that's what we call baryon acoustic oscillations. And they act like a cosmic ruler, a standard ruler we can use to measure, well, cosmic distances, of course.
A ruler. That's pretty ingenious.
Yeah.
So the DSI researchers, they looked for these BAO patterns in their massive galaxy map. And then they compared what they saw to what we already know about BAO from the very early universe, from that afterglow of the Big Bang, the cosmic microwave background radiation, and they also compared it to observations of supernovae, those exploding stars.
Right. Those act as our reliable distance markers.
And it's this comparison, this is what's causing all the stir, right?
Yeah, it's where things get interesting.
Because the way these BAO appear on DESI's map, it doesn't quite line up.
Yeah.
When we compare it to those other measurements, those cosmic yardsticks, well, it suggests that dark energy, the mysterious force that everyone believes is behind the universe's acceleration, it might not have always been the same. It might have actually varied its influence over time.
It's a big idea.
Huge. And this really challenges the current leading theory, doesn't it? We have the Lambda Cold Dark Matter model, CTDM. That's what everyone's been working with. Can you give us a quick rundown of dark energy's role in that?
Of course. DESIDM, it's been the bedrock of cosmology for years. The lambda, that Greek letter, it represents Einstein's cosmological constant. And in this model, lambda, it's treated as a constant.
Like tossed dark energy.
Exactly. It's this form of dark energy that's just uniformly spread out everywhere in space. And it's what's supposedly driving the universe's acceleration.
Yeah.
Then you have the cold dark matter part of the model. That accounts for all the matter out there that we can't actually see, the stuff that doesn't emit light, but it still has mass and it interacts through gravity.
So the article makes this really interesting point. It says that the DSI measurements, when you look at them on their own, they actually fit pretty well with this CDM model.
Yeah, that's the thing.
So if that's the case, then what's making everyone question this idea of constant dark energy?
Well, the real insight, the aha moment, comes when you take the DSI data and you combine it with all these other observations, these independent, really solid observations that we have. Things like the cosmic microwave background, which is like this snapshot of the universe right after the Big Bang.
Right, the baby picture.
Exactly. And then we also have those supernova measurements from when the universe was a bit older. When you put all of that together, the model that fits best, the one that explains everything we see, it's not a model with a perfectly constant dark energy. What it points to, what fits the data best, is a dark energy that's changed over time.
Gotcha. So DSI's picture, on its own, it doesn't necessarily scream, hey, dark energy is changing. But when you put it next to the baby picture of the universe, and then some pictures from its teen years, well, the whole family album taken together, it hints that maybe, just maybe, dark energy has been changing this whole time.
That's the idea.
That's a pretty big shift from this idea of a steady, never-changing cosmic accelerator. It really makes you think.
Definitely. It's making us go back and re-examine some of our most basic assumptions. And to really understand how significant this is, I think it helps to take a little trip back in time. Look at how this whole concept of an accelerating universe even came about. The article mentions the work of Alan Sandage back in 1970.
Yeah, Sandage, he was all about pinning down these two key numbers. We have the Hubble constant, age of which tells us how fast the universe is expanding right now. And then there's the deceleration parameter, Q or K. That one, that was supposed to reveal whether or not gravity was slowing the expansion down. And back then, everyone just assumed, well, it makes sense. Gravity should be the big boss, right? Putting on the brakes, slowing everything down.
Yeah, it was the logical assumption. Everyone thought the universe's expansion, which Edwin Hubble had discovered earlier, well, it should be slowing down because all the matter in the universe is pulling on itself, right? So measuring this deceleration, that was the main goal of cosmology back then. But then in 1997, we had these groundbreaking discoveries by two teams, the Supernova Cosmology Project and the High-Z SN Search Team.
This is Saul Perlmutter, Adam Rees, and Brian Schmidt. Right?
Exactly.
The guys who looked at these incredibly distant supernovae, trying to measure that slowdown everyone was expecting. And what they found, well, it just blew everyone's minds.
It was a huge surprise. Instead of finding a slowdown, what they found was that the universe was actually speeding up.
Speeding up?
Speeding up. This was totally unexpected. And ultimately, this discovery is what earned them the Nobel Prize in Physics in 2011. Their explanation for this acceleration: Einstein's cosmological constant, lambda.
And isn't it crazy that dark energy, this lambda phenomenon, it makes up something like 70% of all the energy in the universe?
Yeah, the vast majority.
70%. It's the biggest piece of the pie, and we still barely understand what it is. And as the article points out, we don't even know for sure if it's really constant.
It's a bit of a mystery. And, it's interesting. Einstein himself, he first introduced the cosmological constant back in 1917. He was trying to build a model of the universe, but he wanted it to be static, not expanding or contracting.
Right, not changing at all.
Yeah. Of course, now we know the universe is expanding, but that's a different story. Later, the physicist Georges Lemaitre, he developed some models that included this constant, but this time in an expanding universe. And these ideas, they're really the foundation for our current ISADM model.
So for a long time, this cosmological constant, it's been the go-to explanation for dark energy and the acceleration of the universe. But now, with these DSI findings, especially when you combine them with other data, well, it's making everyone question that idea of constancy. And the article mentions this paper from 1988 by Peoples and Ratra. What was their take on this?
They suggested something really interesting. They said, what if the cosmological constant isn't actually fixed? What if it changes over time? And it's funny, when they first proposed this idea, it wasn't exactly a hit. The scientific community wasn't really on board.
So it was a bit ahead of its time.
Exactly. But now, all these years later, with more and more evidence piling up, including these results from DSI, well, their idea is starting to gain some traction.
And if dark energy really isn't constant, if it can actually change, that throws open the doors to some wild possibilities about the future of the universe, doesn't it? The article even talks about the idea that this acceleration, it might not be forever.
That's right. It's not necessarily the end of the story. Just like the universe has gone through these different phases, different epochs, like the period right after the Big Bang when everything was expanding super fast, then the radiation-dominated era, and then the matter-dominated era. Well, maybe this period we're in now, this period of dark energy dominance and acceleration, maybe it's just another phase, and if dark energy starts to weaken, well, who knows what could happen?
People have talked about the big crunch, right?
Exactly.
Instead of expanding forever, gravity takes over again, and
Yeah.
everything collapses back in on itself. Kind of like a reverse Big Bang. It's a pretty dramatic alternative to this picture we have of the universe just expanding forever, getting colder and colder.
It's a dramatic idea, for sure. But remember what Carl Sagan said, and it's mentioned in the article too, extraordinary claims require extraordinary evidence. And while these DSI results, they're really exciting, we do need more. We need multiple independent lines of evidence before we can confidently say, okay, dark energy is variable, let's rewrite the textbooks.
That makes a lot of sense. One set of observations, even if it's really interesting, it's not enough to completely change our understanding of the universe. So what's next? What are the next steps in figuring out what dark energy really is?
Well, the good news is that DSI isn't alone in this. The article mentions some other major projects that are happening right now, like Euclid and the JPAS survey. They're both doing large-scale galaxy mapping, but from different angles. It's a global effort to solve this cosmic puzzle.
Feels like we're in this really exciting time for cosmology, almost like a turning point.
Yeah.
The standard model, it's been great, but these new findings, they're suggesting we might be missing a big piece of the puzzle.
Absolutely. It's a great example of how science works. Our understanding is constantly evolving as we get better at observing the universe, as we gather more data. What we thought was solid ground can always be challenged and refined, or even completely overturned if the evidence points in a different direction.
So for you, the listener, the key takeaway here is this. The latest data from DSI, especially when you consider it alongside everything else we know about the universe, it's giving us this really tantalizing hint that dark energy, the force behind the universe's expansion, might not be as constant as we once thought. This isn't just some minor tweak to our theories. It could mean we need to rethink some of the most fundamental ideas about how the universe has evolved and what its ultimate fate might be.
That's it. That's the heart of it. And it just shows you, even our most basic scientific principles are open to revision as we learn more about the universe. And the implications of a non-constant dark energy, well, they could completely change our understanding of, well, pretty much everything.
It's pretty mind-blowing. If the universe might not expand forever, if it could eventually collapse back in on itself, what other constants might be up for debate? What else will we learn as we get better and better at observing and understanding the cosmos? It's a reminder that scientific knowledge is always evolving. Thanks for joining us for this deep dive. Until next time, keep those cosmic questions coming.